Okay, let's follow up, continue our discussion on the sensors for robotics and for that matter for many other applications. So one of the questions, it said, what is GPS? The Global Positioning System is a satellite-based navigation system made up of a network of 24 satellites placed into orbit by the US Department of Defense. GPS was originally intended for military applications, but in the 1980s, the government made the system available for civilian use. Okay. GPS works in any weather condition, anywhere in the world, 24 hours a day. There are no subscription fees or setup charges to use GPS. So it was a gift from America, I guess, for the whole earth. Okay. So now, how does it work? GPS satellites circle the Earth twice a day in a very precise orbit and transmit signal information to Earth. GPS receivers take this information and use triangulation to calculate the user's exact location. Essentially, the GPS receiver compares the time a signal was transmitted by a satellite with the time it was received. Okay? The time difference tells the GPS receiver how far away the satellite is. Now, with distance measurement from a few more satellites, the receiver can determine the user's position and displays it on the unit's electronic map. That's how it works. And in a minute, I'll take you to a website which takes you step by step how these satellites are transmitting, and you pick up your distance from different satellites. So before the smartphone came about, we had to buy these devices and in our car. Remember that? I still have one of them. Oh. Don't use them anymore. So you have that, and the GPS receiver must be locked on to the signal of at least 3 satellites to calculate a 2D position, latitude and longitude, and track movement. With 4 or more satellites in view, the receiver can determine user's 3D position, latitude, longitude, and altitude. You see? That's amazing. Okay. That's why, a satellite, it orbits the Earth, and you could look down to a tower on the Earth and know how tall is the tower. Okay. Once the user position has been determined, the GPS unit can calculate other information such as speed, bearing, tracks, trip, distance to destination, sunrise and sunset time, and more. And as you know from your smartphone, you can basically keep giving you updated information that you are so far from the next turn, to the left or to the right, and what is your estimated arrival time, all that information. And occasionally, if there's traffic jams, it will tell you that too. Okay. How accurate is GPS? Today, GPS receivers are extremely accurate thanks to their parallel multi-channel design. Garmin's 12 parallel channel receivers are quick to lock onto satellites when first turned on, and they maintain strong locks even in dense foliage or urban settings with tall buildings. That's fairly new. In many original GPSs, when you go to Midtown Manhattan or to downtown, let's say San Antonio or Houston or what have you, tall buildings prevent you. to have a good lock into a satellite. Certain atmospheric factors and other sources of error can affect the accuracy of GPS. Garmin's GPS receivers are accurate to within 15 meters on average. Of course, this text itself is 2-3 years old. So I went to this website, and this website is here. You can go to many different aspects of GPS. Why GPS? What is GPS? Oh, triangulation. It is triangulating. Step 1 in triangulation. Improbable as it may seem, the whole idea behind GPS is to use satellite in space as reference point for location here on Earth. That is, light by very, very accurately measuring our distance from 3 satellites, we can triangulate our position anywhere on Earth. Forget for a moment how our receivers measure this distance. We'll get to that later. First, consider how distance measurements from 3 satellites can pinpoint you in space. Step 1. Suppose we measure our distance from a satellite and find it to be 11,000 miles. Knowing that we're 11,000 miles from a particular satellite narrows down all the possible locations we could be in the whole universe to the surface of a sphere that is centered on the satellite and has a radius of 11,000 miles. So you are on a circle with that kind of radius, 11,000 miles. So a second satellite narrows down our location. That's step 2. Next, we measure our distance to second satellite and find out that it is 12,000 miles away. That will tell us that we are not only on the first sphere, but we are also on a sphere that is 12,000 miles from the second satellite. Or in other words, we are somewhere on the circle where these two spheres intersect, right here. We are somewhere in here right now. This was the result of the first lock, the second lock to second satellite. Then now you go to a third satellite. If we then make a measurement from a third satellite and find that we are 13,000 miles from that one, that narrows our position down even further to 2 points. Okay, one's intersection of this and this one and that one, these 2 points. So by ranging from 3 satellites, we can narrow our position just to 2 points in space. To decide which one is our true location, we could make a fourth measurement, but usually one of the 2 points is a ridiculous answer. Either too far from Earth or moving to an impossible velocity and can be rejected without a measurement. So one of them can be rejected. A fourth measurement does come in very handy for another reason, which is the third dimension we saw before. So you can actually go through this menu and look at many different aspects of GPS, and it would be a very useful thing to do. We do have 6 GPS sensors in the lab, and Patrick is, as I said, is putting it on those 4 Kibuki robots and 2 some other track robots. Okay. Here is another angle to this discussion. How automation and robotics will help a smart home. How a smart home technologies can benefit from automation and robotics. So what's the motivation here? We want to look at intelligent environments. Those are aimed at improving the inhabitant experience and task performance. For example, you want to automate certain function in your home. You want to provide services to the inhabitants of your home. So decisions are coming from decision maker or makers. In the environment have to be executed. Decisions require actions to be performed on devices. Decisions are frequently not elementary devices interaction, but rather relatively complex command. So decisions define set points or results that have to be achieved. Decisions can require entire tasks to be performed. So how do we automate with the help of robots in so-called intelligent environment? Control of the physical environment, like automated blinds on your windows, thermostat and heating ducts, automated doors, automatic room partitioning. Or you could have personal service robots, house cleaning, like Dr. Benavides' robot, lawn mowing, assistant to the elderly and handicapped, office assistants and security services. Of course, you already know Roboto came as a Czech word in 1921, was a playwright, Czech playwright Karel Čapek, called Rossum's Universal Robots. Then, of course, the Japanese Industrial Robot Association, a device with degree of freedom that can be controlled. That's their definition of robot. It can do manual handling devices, can fix sequence robot, it can be variable sequence robot, playback robot, numerical control robot, intelligent robot. So, in the 14th and 16th, up to 19th century Europe, you have what's called a clockwork driven for entertainment, like here. And in the ancient Greece or Egypt, you had water power for ceremonies. And motor-driven robots, 1928, first motor-driven automata. 61, you know, Unimation and Unimate robot in America, first industrial robot by the good work of my late mentor, Dr. Engelberger. 1967, Shaky was created, was autonomous mobile robot in the US. 69, a Stanford arm was a prismatic and revolute combination of joints. It would rotate and would go in and out prismatically, and they were all worked there. And these are many different robots. You have manipulated robots here and here. You have mobile robots, wheel robots, and you have space robots. This is a picture of the Sojourner robot, which landed on Mars on July 4th, 1997. Then, of course, you have walking robots, locomotive robot, humanoid robot. Okay. Autonomous robots. The control of autonomous robots involve a number of subtasks, understanding and modeling of the mechanism, that is kinematics, dynamics, odometry. Again, odometry is the fact that the robot never reaches its destination. You have to estimate its location continuously with the help of vision or Kalman filtering and so forth. Reliable control of actuators, closed-loop control. You know, control is always a necessary part of everything you do. Generation of task is specific motion, path planning. You need to plan your path so you don't run into obstacles. You don't hit another robot. You don't get to the location where you would fall down. Integration of sensors, sometimes called sensor fusion. That is a tough cookie. You have information coming from many sensors, they integrate with each other, you got to make sense out of the result. Okay. Generally, it gives you more information, but you have to have techniques and tools to be able to infer the information that you need. Selection and interfacing of various types of sensors. Coping with noise and uncertainty, filtering of sensor noise and actuated uncertainty, which are two elements of that mathematical formulation that your author has done for the chapter on locomotion. Remember, two different Gaussian white noise distribution for those two uncertainties. Creation of flexible control policies. Control has to deal with new situation, which means the controller has to be adaptive, has to adapt itself to changing environment. It could be because of unmodeled dynamics in the model of the robot or your system, or it could be changing scene, changing environment, especially if you're dealing with unstructured environment, like web, like surface of Mars, but you don't know what's going to be, what's going to be in front of that robot the next hour and the next day. So these are traditional industrial robots. So in a way, this lecture is also reviewing the course for you. Okay? So I'll be talking about different things next week. So you have repetitive tasks, you have high speed, you have few sensing operations, high precision movements, pre-planned trajectories and task policies, no interaction with humans. So the robots, as you see here in red, are doing a specific work on body of a vehicle on the conveyor belt, and you program it, and it is there working for you day in and day out without striking, okay, without asking for a raise, nothing like that. And it's there until your manufacturing lane changes. Then you have to reprogram it and so forth, and you go after it. Traditional programming techniques for industrial robots like key capabilities necessary for intelligent environment. To be honest with you, a lot of times for manipulated robot, which has a specific task, which are mundane and pre-assigned and pre-programmed, you don't need a whole lot of intelligence. Because they are dealing and working in known environment, known workspace. You know exactly to the last dimension how far that robot is going to go this way or that way, or up or down. You know the workspace. But it's a mobile robot which you have to worry about, going to an environment it hasn't seen before. So, no incorporation of uncertainty, no interaction with humans, reliance on perfect task information, complete pre-programming for that. After all, you're manufacturing something you want to sell to somebody, and you cannot sell it, you're not doing it right. But so those uncertainties have no room for a factory floor robot. Requirements for robots in intelligent environment. Autonomy is a very important part. Robots have to be capable of achieving task objectives without human input. They have to be able to make and execute their own decision based on sensor information. Okay. For example, sometimes I was challenging my students in the following way. I I wonder if camera can come here. Suppose this is the surface of the Mars, and you have two rocks, one rock here, one rock here. Bharat, could you focus on here?
Yes, please.
Okay. And you are going to go to point B from point A. You want to go from point A to point B, you're on surface of the Mars, and you have no human to help you. Your robot is moving like this, and the robot goes there and cannot fit in between two rocks. So what are you going to do? So it has to have enough intelligence to know that this is too narrow for its dimension. And it has to find an alternative path to go to the. We have actually programmed this and simulated that in some of our projects with the students. So you need to have sensory information, be able to make decisions without the interference of the human. Okay? Back to the slideshow, please. So robots have to be able to make and execute their own decision based on sensor information. That's the example I mentioned. Intuitive human-robot interfaces. Use of robots in small homes cannot require extensive user training. So an elderly doesn't need to learn robotics and other interface, sophisticated things with the robot. Okay? And commands to robots should be natural for inhabitants, natural language. And adaptation is another requirement in those environments. Robots have to be able to adjust to changes in the environment, as we said before. For example, on the Mars or on a place where you have not yet seen before. So those are some robots for intelligent environment, service robots, security guard, delivery robots, cleaning robots, mowing robots, assistant robots for mobility, for service for elderly and people with disabilities. So you can see here a very sophisticated robot that we are trying to build in the ACE field lab on a walker. But this one is, you've got a big, a huge server in the back of it, and a big manipulator here. And it's probably cost a huge amount of money. Yeah. So we want to make it functional, easy to use, and affordable. Hopefully, Nico will achieve that. Now, for the autonomous robot control, to control robots to perform tasks autonomously, a number of tasks have to be addressed. Modeling of robot mechanism, kinematics and dynamics. And when you do that, like every mathematical programming, rather mathematical modeling tool, as you already know, some of you are graduate students, you have gone through these things. When you model a system, you are buying inaccuracy and certainty. Because the physical principles of physics, mathematics, and so forth are not 100% compliant with the nature of that real system. Okay. So, and very often you may have to make approximation, assumption, which is counterproductive in terms of accuracy of the model. So a lot of times you can make so many assumptions, by the time you come up with a model, it's so far from reality. Then it would be useless to use it. So if you base your control laws and control paradigms, based on that inaccurate model, you're bargaining for headache. Your control is not going to be good because in real system, the system changes. Its dynamic is really not representative already on that model. So you are dealing with unmodeled dynamics. And some modes of that system are going to be excited by control signals which are not accounted in the model. And I think I may have mentioned that to you before. A space station which is rotating around the Earth as I speak right now is an infinite dimensional model which you cannot model. It's an infinite dimensional system. It has thousands and thousands of joints, actuators, sensors co-located. If you want to model all of them, you have to have infinite number of state variables and sensors. So what you model, you reduce it to a lower dimensional model. And in doing so, you better know what you are doing. Meaning that you retain those modes of the system which are the dominant modes of the whole system. So you are counting for 95% of the modes, you could afford to forget about 5%. That's the point. And then you can make the control not only cognizance of those unmodeled dynamics, make the control to change its own behavior in view of those changes of the model. In other words, do an adaptive control. You have a basic control, you have a second controller on top of it as a supervisor to control the controller. Then you're going to be sort of adjusting yourself in real time. So low-level control actuators are the ones which you can control based on the mathematical model, and then you have supervisory on top of it. Okay, you have behavior-based control architecture and hybrid architecture. Those are what I'm talking about. You have more than one controller, one local, one global. Okay, that's what we're talking about. Modeling of robot mechanism. Forward kinematics, you know. So once again, what is forward kinematics? Given a bunch of joint angles, where am I ending up? Inverse kinematic, given a position in the free space, what kind of joint angle do I have to move around, to go around? Here, this way, that way, all way, until this. Okay? Which is much more difficult problem and has a lot of issues, like singularities and others. Jacobians that we discussed last week, Jacobians calculate how the speed of and configuration of the actuators translated into velocity of the robot. Okay, so again, in your preparation for the exam, you can prepare yourself. These are some of the basic fundamentals of your final exam: Jacobian, inverse kinematic, forward kinematic, and so forth. In mobile robots, you need to worry about odometry. In other words, I'm located at point A. I know where I am. I know where is my orientation, and I want to go to a new location based on my old location. So here's my new location, x, y, and theta, based on the old one, and then the amount of time it takes for me to go from A to B with this velocity, and this velocity. Okay? This is like a differential derived robot you saw before in the previous slides. You have two velocities to be your control signal. Okay? And then states are x, y, and theta. It is this estimation which a lot of times is missing the target, and you occur an odometry error, and which you have to compensate for it, as I said, through several cameras or vision, or you compensate for it based on filtering like Kalman filtering and so forth. Actuator control, you are a basic control mechanism like a PD controller. The most common control is the PD controller. Proportional product derivative, or it's called a differential controller. You have the error in the desired to the actual position multiplied by its gain, Kp, and the same thing for the velocity, and do that. This is a very sound controller for actuator which is located inside the robot, right on the robot, and uses internal sensors to do all of that feedback. For navigation, you can go both in and out of the environment of the robot. You do path planning, addresses the task, completing a trajectory for the robot that reaches the desired goal without colliding with obstacles. You could have optimal paths are hard to compute, in particular for robots that cannot move in an arbitrary direction. That is to say, non-holonomic robots. They have to have a specific path they can reflect back on it. Shortest distance paths can be dangerous since they always graze obstacles. Paths for robot arms have to take into account the entire robot, not only the end effector. Sensor-driven robot control. To accurately achieve a task in an intelligent environment, the robot has to be able to react dynamically to changes in its surroundings. Robots need sensors to perceive the environment. They need to use a set of different sensors for different purposes. We've seen a lot of them already today. Information from sensor has to be integrated into control of the robot. You saw that already for encoder. Here is another visit of the encoder, how that works. This is incremental, and this is absolute encoder. More of the robot sensors, proximity sensors, infrared sensor, ultrasonic sensor, laser rangefinders, all of those. Let me see. Here you send a wave to obstacle, and it gets bounced back to the robot or observer, and then you will find out where you are located. So here is triangulation. Computer vision provides robots with capability to passively observe the environment. Stereo vision systems provide complete location information using triangulation. You have two cameras looking at the same object, and you have two distances here. You know what this distance is, then you know everything else. If you know two sides and an angle, you're okay. If you know all three sides, you're okay. You know exactly where you are. However, computer vision is very complex. Correspondence problem makes stereo vision even more difficult. That's why, again, this kind of vision is not very good in outdoor. Okay, and GPS is you have a better chance. So, what are the uncertainties in robots? Robot systems in intelligent environment have to deal with sensor noise and uncertainty. So, sensor readings can be imprecise, can be unreliable, and you could also have non-observability, meaning various aspects of the environment cannot be observed. The environment is initially unknown. So you have problem knowing what you are looking is, you are not sure what you're looking at. So action uncertainty also follows that. Actions can fail, and actions have non-deterministic outcomes. In other words, you're waiting for a disaster, potential disaster. probabilistic robot localization. Again, you can, as we said before, you can have, by way of localizing yourself, finding where you are, you can gradually build a map around you. Like we talked last week, you can build a map around yourself. Let me see what else I can. Deliberative control architectures. I don't know, these are not useful. Behavior-based robot control. Behavior-based is a class of control methodologies, which actually my students have done in the past, in previous position I had. The idea started with Professor Rodney Brooks at MIT about 20 years ago or so. The idea was this: if a mobile robot is moving in an environment, what are the most basic movements and motion of that robot? For example, the robot is going to be following a wall. That's very primitive. A robot may counter an obstacle, it has to avoid it. Okay? And robot has to watch out for their bodies and other robots not to run into them. Those are primary behaviors. When you move to another level, it becomes more complicated. We call it compound behaviors. In that level, you are actually doing something useful with the robot. Okay? Or you go all the way to another, even more complicated compound behavior, where the robot has to get out of this door, let's say. It's going to have to get out of this door. Imagine that a mobile robot trying to get out of this room, and you close your eyes and try to get out. See what happens. You need to hit. You're going to do some primary work. You're going to go around the wall, and you could go run into that chair. You try to avoid it, and so forth and so on. That is behavior control. Rodney Brooks at MIT did expert system, classical logic. We extended it to fuzzy logic control, so that you could have some inaccuracies in the process, but you still achieve the same task. Okay. So my time is almost up. So the rest of these are review. We'll discuss it next week, and I hope that you are continuing working on your homework number 4, and I'm looking forward to seeing your homework. See you later.